Hello, everyone. My name is Andre Santos, and today I will be presenting our work on schema-guided testing of message-oriented systems. Let me start with the problem we are facing. As software systems grow in complexity, it becomes hard to manage all of their capabilities. Modular architectures are a common solution to this problem. Features are assigned to isolated components, which are later integrated into a larger system. The components communicate via message passing, and may even be developed by third parties. But testing this kind of message passing system is not an easy task. First, the components may be very heterogeneous, probably even implemented in different languages or platforms. Second, some of them may also be closed source, meaning that we have no access to their internal behavior. And third, these systems may be distributed over a network, with asynchronous publisher-subscriber communication at their core. Thus, considering all these obstacles, the most reliable way to test message-oriented systems is to describe the system's behavior in terms of the exchanged messages during its operation. This has the advantage of treating all components the same way, as black boxes with an exposed interface. This interface is often built on top of a common middleware or framework. But how is the testing done, in practice? Building test cases by hand is good to ensure that a few special cases are captured, but is completely unfeasible in general. There are too many edge cases and message interleavings that one does not consider or does not have the time to write down when writing tests. Automatic test generation is more appealing, and there are many methods to do it, but each comes with its own challenges. One of those challenges is that, quite often, using these techniques requires expert knowledge in formal methods, which is something that most testers will not have. Besides, there is still a considerable amount of work that goes into modeling, writing properties, and so on. Work that has to be carefully checked for mistakes. In addition, some corner cases might not be caught with automated testing. It is better seen as a complement for manual testing. But let us have a closer look at some of these techniques. Specification-based testing, for example, is a black box testing technique. It does not care about how a component is implemented. Instead, it takes a list of formal requirements, and, from the structure of each formula, it identifies relevant classes of inputs that should be tested. Then, if we provide an example input for each input class, we should have covered all the specified behavior. Next, we have property-based testing, which some of you might know, in other contexts, as fuzzing. This technique uses semi-random input generators to test a feature multiple times, until either a bug is found, or a maximum limit of examples is reached. In this case, properties are encoded programmatically, rather than with logic formulas. You might have noticed that one technique is more high-level, while the other is more low-level. Combining principles from the two techniques, we get schema-guided testing, the approach that we propose in this paper. With specification-based testing, we identify interesting, high-level classes of inputs, or testing strategies, that we call schemas. With property-based testing, we explore multiple inputs, in a semi-random way, for each identified schema. In addition, we propose a user-friendly approach that takes into account a high-level specification language that abstracts away the formal semantics and logic formulas that make it all work. This language is based on the famous specification patterns by Matthew Dwyer, and is capable of expressing constraints both over data and over real time. Let me illustrate how it works. The user starts by providing a specification. This document contains two things: the system's architecture, components and communication channels, as well as the properties we want to test. The user also provides the system to be tested, obviously. From the given specification, we are able to convert the properties into trace schemas, high-level templates for the traces of messages that we want to replay to the system. Additional properties of the inputs, called axioms, may be taken into account to refine the generated schemas. From these schemas, or templates, we instantiate multiple, concrete traces of messages. These messages are replayed to the system under test, under a testing loop. And any property violations are detected using runtime monitors as oracles. These monitors are also automatically derived from the specification given by the user in the first step. Finally, any detected bugs are reviewed by the user, so that they can fix either the system or the specification, and start over. Let us now take a closer look into the specification. Starting with the architecture, we expect a list of components and their communication channels. From this, we should automatically detect which channels are open, that is, which channels are subscribed, but have no active publishers. These are the channels that we will consider as system inputs. Other channels may be observed, but we will not send messages to them. Then, we also have the properties. Properties have two components: a scope and a pattern. Scopes define when a property should be valid. Should it be always valid? Or maybe only after a certain message or system state is observed? The patterns are used to construct the property itself. What are we trying to specify? It could be that a particular type of message should not be observed within the scope. Or, maybe, that one type of message causes another message to be published, further down the line. Each of these patterns has a timed and an untimed variant. But let us take a look at an example. Suppose that we want to test a mobile robot. And we want to make sure that, when the laser detects an obstacle closer than 40 centimeters, a zero-velocity message will be published, within the next 500 milliseconds. This is how the property looks with our language. Globally means that the property should always be true. And it is always the case that a laser message, with a distance less than 40, causes a zero-velocity message within 500 milliseconds. Let us now see how this high-level property is converted into a trace schema. Our first step is to convert these properties into logic formulas. Our language is backed by formal semantics, based on metric first-order temporal logic. We have defined a translation for each scope and pattern, that happens transparently to the user. Then, from a logic formula, we are able to derive a test strategy. This is basically a template that captures the structure of all counterexamples for this type of property. In this case, any counterexample must have at least one laser message with a value less than 40. So the schema starts by disabling such messages until a certain point when we publish at least one, that we want to track. We can add additional properties over the input channels, that we call axioms. For example, we can state that the laser value should not be negative. In some cases, these axioms are automatically incorporated into the schemas, refining them, as we can see here. Now, going from schemas to actual traces of messages. The first step is to allocate all mandatory events. In this case, we have only one. We select an arbitrary timestamp, starting from the beginning of the trace. Then, once we have all mandatory events, we start generating random messages in between. The random messages will take into account those forbid statements. For example, we do not want to send more laser triggers before the one that we want to track. But we are free to send other messages, to lead the system into different internal states. Finally, we do the same for the interval after the mandatory message. But, in this case, we can allow more laser triggers. We have ensured that we have at least one, which is what matters for a counterexample. This process is repeated, over and over, using a property-based testing library, and appropriate data generators, that we produce from the specification. This approach has been implemented to test robotic software developed with the robot operating system. In particular, we have used two robots, the Turtlebot 2 and AgRob, as case studies. Furthermore, we have implemented our approach as a plugin for Heros, an analysis framework for ROS software. The advantage of integrating our approach as a plugin, in this case, is that Heros is already capable of extracting the software architecture, automatically, from source code. Thus, this makes the life of the user quite easier, because they have to provide only the properties by hand, not the architecture as well. In addition, all analysis reports and test results are presented in a unified user interface, which is another bonus in terms of usability. Our evaluation of this approach used positive and negative testing. The former is to test true properties and to find no errors. The latter is to test false properties and find the expected errors. We wrote down true properties first, and then generated a catalog of false properties using specification mutation. Basically, making small changes in the original properties, like changing comparison operators, that make the properties no longer valid. This is more or less equivalent to mutating the software, and always testing true properties, but is quite easier to do in a reasonable amount of time. Our testing has found no false positives, resulting in a precision of 1. As for the negative testing, we made various testing rounds. First, with a limit of 200 input examples per property, and achieving a recall slightly above 90%. Then, by raising the limit up to 500 examples, but this did not improve the results by much. In another round, we improved the axioms we were using, making them stronger and more limiting in terms of allowed inputs. This already showed improvements at 200 examples, raising the recall to nearly 93%. Once we also pushed the limit to 500 examples, with the improved axioms, the tool was able to find all counterexamples. So, summing up, testing message-oriented systems is a hard endeavor, but combining automatic testing techniques looks to be a very promising approach. Especially if high-level specification languages come into play, to make these techniques easier for normal users to grasp. In terms of future work, We will be exploring a few different directions, such as breaking the generated schemas down into smaller pieces that may allow us to explore parallelism. Another useful improvement will be to improve the automatic schema refinement system, that, for now, is only capable of handling a few types of axioms. Lastly, the specification language itself can be improved, by adding more patterns and constructs to it. And thus, this presentation of our work, titled Schema-Guided Testing of Message-Oriented Systems, comes to a conclusion. I hope that you found it interesting, and I thank you for your attention.